Okay, hi, I'm here to talk about the asymmetric encryption schemes and kind of the mathematics behind them, the core mathematical ideas, and how they're used for some really important cryptographic steps in modern cryptography. All right, so it does start similarly to a symmetric key idea. So they're an algorithm, so a machine basically, and they do create permutations. So 0, 1, 2, 4, 5, and then 2, 3, 4, 0, 5, 1, for example. Okay, so this is a permutation, so it's a list of numbers to the same list of numbers where you don't repeat anywhere. That way, every time I see a number here, I could figure out what it corresponds to by going across, okay, and I can go backwards, all right? So not all algorithms are permutations, but the ones that we're talking about for this part of cryptography are creating permutations, right? And then again, in the real world, this list is quite long. 2 to the 256 is not unreasonable, and I mentioned just how ridiculously big that number is, okay? So the idea then is this permutation from numbers to numbers like this, all right? And then this algorithm is this machine that can go this way and that way, all right? So the symmetric key idea was that basically going from an unlocked state to a locked state, so the specific permutation was given by a single key, and going from here to here was applying it in the first direction, and then using that same key you could also reverse it and go from the code on this side to the code on that side. And using that as a mechanism, if you had the key available to you, then you can both choose to encrypt and decrypt. You just have to make sure that both ends, whoever you're trying to share information with, have that information. So they both have the key in that case, then you can create messages between each other. So in the new scheme though, we'll separate those two steps away and say that there's something called a public key, which makes it easy to go that way, or reasonable. It's a sort of a small amount of computation to use a public key and go from here to here. But the private or secret key, and people call it either way, slash secret. So if you want to go from this side to this side, you need the secret key instead. All right, and the analogy then that I was using as a physical device is these kinds of locks. And what's nice about them is you can be in the unlocked state, right? And so you could have this on a board somewhere anybody could pick up, right? And say, okay, I want to send a secret message to Bob. Here it is in its unlocked state. I don't need to know the key in order to, I don't need to know the private key. I just have to have the public key, which is this little machine right here. So I have this public key. I can use that to lock and create something on this side, all right? So that's the public key idea. But then the private key, so once it's over here, it would be very difficult to go back unless you possessed some extra piece of information that's called the private key. And that extra piece of information lets you take this and go back to the original that way. So with the private key information going this way is reasonable. It doesn't take a ridiculous amount of computation. But with the public key, you can go that way, all right? Some mathematics of how those work is interesting, but let's just say for the moment that that's true. And there's some ideas, some mathematical ideas, like you do this, where you can put some public information out there that by themselves you can't easily reverse this, okay? So with this scheme, you certainly should be able to do the same thing you could do with the symmetric key idea, right? Because, well, I just demonstrated it, right? You can take information, write it in terms of these codes, and then take the codes, and then anyone with access to the public key, which should be anybody, can use this machine and translate it into this information. So that's this idea of locking, right? And that's just no access to the key. So this is just the public key and locking something on that side, right? So if you have that, you can send information that now you know that only Bob can unlock, apparently. And so you need a private key. Hopefully Bob is the only person that has the private key. So Bob can then unlock on the other side. And so they can go back, the unlocking step is to take the algorithm, do this step and go back to the original. So you can take codes that represent something that maybe, you could look up what each word or each sort of code book thing means, and then send it over to a bunch of scrambled codes that people wouldn't be able to decipher unless they have the private key. Then Bob hopefully is the unique person, has that private key, and then they can recover the original codes to do the decoding step. So in the symmetric world, both those use the same key. And so one question I think you're not sure, like, why don't we always just do it this way? And the important thing is these algorithmically are plausible, but they take a lot more computation than the symmetric ones. And so even though it really means the difference between kind of microseconds to milliseconds, it really is hundreds or thousands times more work to operate these keys compared to the symmetric ones. And so usually what happens is right away you use one of these schemes to share a symmetric key, and then you jump to one of the symmetric schemes and then share all the other information that way. So initially, to kind of get the ball rolling, you use a scheme like this, and the secret you actually share is the secret key, the private key, the symmetric key for a symmetric scheme. So you use a scheme, and the secret you're actually just sharing across here is like, here is the code that I plan on using for some symmetric scheme, which is just fast, and then all the rest of my information I'm going to send that way. Okay? So they are just generally like, they're just better because they do the old thing plus a new thing. But what makes them worse is that they're just computationally more expensive. That doesn't mean hundreds of years kind of expensive, but it does turn sort of like, millions of seconds into thousands of seconds. And if you're doing lots of encryption, then that's a lot, and so you'd rather like have the fast way instead. Okay, so certainly then you can pull off encryption, but you can actually do something else, and that's something called signing. So you can't do signing with just a symmetric key, but you can do something called digital signatures when you have this kind of thing available to you. And one more tool, which is called a hash. So let me try to illustrate that. So this is, I guess this is the side of Bob. So Alice is usually on this side. That's the person trying to send information. So Alice is the sender, pretty typical sender. And then here's Bob on this side, who's supposed to be the recipient, or in this case, the signer. So recipient or signer. The one that wants to sign some document that then somebody out there can verify. All right. So what happens? So the first step is you take the initial document, whatever it is, and you compute something called a hash. And you will see a video of how that is done. But basically, for every document, it comes up with a number on this list. All right. And if you pick two different documents, the number will be different, almost guaranteed. So mathematically, it would be impossible, just like guessing two cards out of that billion, whatever tall stack of cards. It would be that hard to figure out a hash or document that matched up to the same hash. So for any document, you can compute their hash. You put like the date or something out here at the bottom, so they're all different. You can't do replay attacks, and so each time you get a hash, it's like, oh yeah, on Tuesday I made this document. Here's the hash. All right. You take that hash, that turns into one of these numbers on this side. So whatever the hash is something on here. Let's say it's number 5, right? So say the hash in this particular, for this specific document, turns out to be the number 5. All right. And then it's Bob, okay, Bob has his private key, which means he can run this thing backwards, and so instead of 5 public key, so that's the second one from the bottom, so that one goes to 4. So over here he puts down, he doesn't have to write the hash down because anybody can compute that from the original document, but he could, and there's no harm in writing it down because it's public anyways. So he puts a hash, and then the signature is actually the number 4 in this case. So because this runs backwards, if I can use the private key, I can use a private key to run it backwards and get to the number 4. All right. So this is that magic thing about nobody else can do that. So anybody can take this public document, okay, and compute the hash. All right. And then when they have the hash, all right, that's like if you're given the document, anybody could do that. All right. Given that, all right, only someone with a private key can take the number 5 and figure it out that it goes back to the number 4 on this side. So being able to write down the number 4 on this thing is proof, what's called mathematical or statistical proof, that someone had access to this private key to reverse this machine. All right. So the signing is to be able to figure out, well, what's on the lock side. I know what I want to get to is a 5 in this case. And then since I have the private key, I can unlock it and realize, oh, the number 4 is, if I lock it, the number 4 is going to end up on number 5 over here. So what's great about that step, right, is only the person in possession of the private key can lock it. But now anybody can take this number 4 and with the public key and unlock it and realize, oh, I'm sorry. Anybody can take an unlocked key, this is the action of the public key, can start from the unlocked state, the number 4, and then use the public key to realize that that goes to number 5. So anyone can go this way that has access to the public key, which should be a lot of people, but only people in possession of the private key would be able to take this and realize that 4 is a place to start. Okay, so how does Alice verify a signature? So this is making the signature. All right, if Alice wants to find out that that Bob signed something, well, they have an exact, apparently what they were to sign, they have the exact copy of it, right, along with the date, so it's not a replay. So they can compute the hash. And because it's exactly the same document, you'll get exactly the same hash. So in this case, they get exactly the number 5. All right. So same document, same unique date on both sides, and compute the hash. And so both of these things can be done by either Alice or Bob and get to the number 5. All right. So there's number 5. All right. But Bob publishes the signature. So here's the date, right? And now the signature is the number 4 over here. And so now, so Alice could go through this step to get to the number 5. So hash of this thing is the number 5. Hash of this thing is the number 5. All right. But using the signature, using this number 4, Alice can go that way, right? Using this scheme, Alice is allowed to go that way, not allowed to go that way. So Alice can take this number 4 and because they started from this side, this is the number 4 on this side, then they can apply the public key and realize, oh, that goes to the number 5. Well, look, these two, that's what it says is going to happen. So only Bob could solve this puzzle to write it down. So only Bob can reverse the 5 to turn it into a 4. But anybody can turn the 4 into the 5. So this is the public key. So the 4 gets turned into a 5 using this algorithm, using the public key. And the only way that could have worked out is if whoever found the signature, who had the signature, had to have the secret key, because there's no other way to reverse this machine. So going backwards in order to come up with this signature requires essentially you're proving that you know how to reverse this machine. So taking the hash and then reversing the machine gives you a signature, right, with just this one pair. And then to prove on the other side that someone did sign, well, anybody can compute the hash. And then with that number, they can then verify that the signature provided by Bob does in fact map. So they can take this signature, which is on this side, all right, and map it using the public key to go to that side. So this permutation scheme allows you to do what's called a digital signature. Some interesting things about that compared to the standard, like just write your name on a check idea, is this only reveals the public key. So using the public key, you can go from the signature and get to the hash, and therefore prove to yourself that the only way someone could have come up with this number is if they had the lock. But it doesn't actually reveal anything about the private key. So unlike a check, or a lot of places, or a document where you see a signature where someone else could like try to forge the signature, it's really not forgeable. It's because the date's on here, you can't replay the document, you can't use it again somewhere else. And because you're only using the public key in public key ways, it doesn't really it doesn't reveal any interesting information about the private key. And so it allows you to sign something in a way that mathematically proves you own a private key. Hopefully you don't let that go, like that Bob keeps it a secret for himself or herself. And it's much stronger mathematically than like the standard signature, which would then allow someone to like, oh, well, since I know this, I can start duplicating it and putting it on other people's checks or something like that, or contracts. So once you break apart this way versus that way, where that's reasonably easy and this is hard, unless you have let me say it a different way. This is essentially impossible unless you have the secret key. So easy with the public key, and then easy with the private key that way. So if you have a mechanism, an algorithm that it works that way, then with that tool, you can certainly do encryption, decryption, but you can also do signing of documents. And so that's really nice if you want to make sure that documents showed up that actually belong to the people that they say they do. So this sort of signature scheme is an interesting part of the whole cryptographic world of proving and knowing what came from where. Okay?